Okay, so we just saw a reaction in which we went through a carbocation intermediate. So we took something like this, we treated this with HBr, we're going to protonate the alkene to make a carbocation intermediate. I'm just going to show the best one, or the better one, the secondary carbocation. And we said, what happens to this carbocation? Well, there are always two fates to carbocations. You can get attacked or lose a beta hydrogen. Well, we know there's a third thing that carbocations can do. It doesn't get rid of the carbocation, but we also know that there are carbocation rearrangements. And we need to be on the lookout for carbocation rearrangements in any reaction that forms carbocations. So when we add HX to an alkene, we need to be aware that carbocation rearrangements can occur. So let's see an example of this. So let's take this alkene and react it with, let's do HCl. We haven't seen an HCl. So HCl, again, it's a strong acid. The alkene is going to be protonated by that acid. It's going to pick up that proton. That proton specifically is going to go over here on the less highly substituted end of the double bond so that we can form our carbocation on the more highly substituted side. Now, this carbocation is a secondary carbocation. Secondary carbocations aren't necessarily as stable as other carbocations, namely tertiary carbocations. So here's a case where if this molecule can undergo a rearrangement to form a tertiary carbocation, we're going to see it. And this carbocation will. So this carbocation is next to a CH bond. The sigma bond of the CH bond is going to hop over, it's going to drag the hydrogen with it, over to this carbon. And as we move electrons in the molecule, we're also going to move the position of the positive charge. And so we will go from having a secondary carbocation to a tertiary carbocation. Be sure you understand this mechanism. I think carbocation rearrangements are hard mechanisms to see. I don't normally think of hydrogen atoms with their electrons hopping around a molecule, but they do. So we now form a new carbocation. It's even more stable carbocation. Now, this carbocation opens up the same conversation. What happens to carbocations? They either get attacked or they lose a beta hydrogen. In this case, we have a nucleophile around. We will attack and we will form our addition product. So for this particular alkene, you might expect, just based on the way it's drawn, that we would form this halide. That's the Markovnikov product from adding to this alkene. But as you think of this expectation, you'll realize, oh yeah, we're going to go through this particular carbocation. But that carbocation is secondary and it has the possibility of rearranging to a tertiary carbocation. So here is our rearrangement. It's called a hydride shift. And that results in forming a new carbocation, which is ultimately what gets attacked to form our final product. So this is our observed product. And this is not our observed product over here on the left. So carbocation, anytime you form carbocations, be on the lookout for potential rearrangements. Don't just assume you're always going to attack or lose a beta hydrogen, because rearrangements are a possibility.